Alrighty, so when you have an intersection of a set of inequalities, it's basically like you're saying you have two of them. Okay, we're going to dive into this one a lot in chapter 4, the next chapter. We are going to talk about inequalities and their solution sets. But since we're right here, we have inequalities, I kind of want to show you this overlapping idea as a little bit of a foreshadowing for that. Okay, so here we've got the inequality 2x plus 4y is greater than or equal to 5. I can tell right off the bat this xy intercept not going to be super nice. Like 2/5 is not a good xy intercept. So I'm going to go with the rearranging idea. Okay. So I'm going to rearrange this one into 4y is greater than or equal to negative 2x plus 5. Y is greater than or equal to negative 1/2 x plus 5/4. Yeah, that y-intercept also really not that great. That's $1.25. And notice the sign did not flip because I didn't divide by a negative 4, I divided by a positive 4. And I got 2/4, which reduces to 1/2. Okay, so let's go ahead and graph that. Notice I'm basically just ignoring the second one for now. I'm just graphing one of them. Up 1.2 is like there, give or take. And then down 1 and over 2 is like that. Okay, now be careful not to go all the way down, right? You're not going 1.2 down, you're going down 1. And this is a solid line. Okay, and it's much more convenient in this format. I noticed it didn't change. I don't have to test a point. It's just shading above, right? Now I'm not actually going to shade yet. Okay, here's where it starts to get just a little bit different. I'm actually going to graph both of these and then shade where they are both true. So let's look at x is greater than or equal to 1. That's one of those special equations. That's another part of this section that's really nice. We get to look at these special types of equations. X is greater than or equal to 1. If I were to graph that like it was equal, that would just be x is equal to 1. If you recall, that's the special line. Special is kind of it gives it too much power. It's just unique. It's just kind of like the weird one. That's a vertical line where all of the x's are equal to 1. Well, here's where x equals 1. Here's where x equals 1. Here's another one. But it is also equal to, so a solid line. All right, now if you do have the opportunity to have an eraser or something that's easily erasable, you can do what I'm about to do. But the greater than section of this would be over here to the right. Okay, I'm trying a big old sushi. And then the greater than section of the purple one would be everything above. The only thing we actually want to shade, though, is this zone here that is both of them. So rather than getting really ugly really fast, I'm just going to shade that intersection trapezoid thing. Okay, just this top corner. It's still it's still the same way to decide. You can do what we just did, decide where it's both greater than, but if you're unsure, you can always test a point. So let's pick a point in that one. That was 3, 3. And I got to test it in both. The second one's kind of easier to test. Is 3 greater than 1? Yes, 3 is greater than 1. So that one works. Check. Checking 3, 3 in the other one. 3 times 2 is 6. 3 times 4 is 12. 6 plus 12, pardon me, is 18, which is definitely greater than 5. So it's true for both of them. Check. If it was true for one but not the other, then you'd probably be in either this zone or this zone, which is still not the area we want to shade. So it's got to be true for both of them. Okay, it's got to be the solution set where they are both true. Hence their intersection, their crossover, their true and true zone. Okay, let's try it again. So we've graphed this first one already. Actually, we've graphed both of these. So now we're going to graph them on top of each other. And we're going to, 9/15 is kind of gross. So I think I'm going to rearrange this again. I think we already rearranged. These were both the ones we rearranged, right? We have y, 3y. is less than or equal to negative 9x plus 15, which becomes y is less than or equal to negative 3x plus 5 equal to, so up 1, 2, 3, 4, 5, and then down 1, 2, 3 over 1, down 1, 2, 3 over 1, down 1, 2, oops, down 1, 2, 3 over 1, and we get this solid line here. All right, and then we can rearrange the other one. We have negative 2y is greater than 8 minus 4x. If we move that 4x to the other side, now I have to divide by a negative 2, and so I'm actually going to turn around my sign. I get negative 4 plus 2x, or if you prefer, 2x minus 4, but it is a less than, not a greater than. So we'll go to minus 1, 2, 3, 4. Up 1, 2, up 1, 2, up 1, 2, up 1, 2, up 1, 2. Okay. And this one, I got to be careful. It's strictly less than. And so we use a dotted line. Okay. For red, it's less than. Red less than would be to the left. For purple, it's less than. And that would be actually to the right. And so we get this section down here. Now you're like, what the heck? Why on earth would less than be right and left and da-da-da? It has to do with the slopes. See how this slope for the red one is going down? And so the things that are less than that are going to be the stuff that's below that negative slope, which would be these points right here, right? Same idea. This slope's going up, so the slope that is less than that would actually end up being this stuff right here, okay, the stuff that's below it. It's kind of hard when the lines are almost vertical, right? But that's where we can always fall back on a test point. We can always just pick a point in the zone we think might be correct, like this guy right here, out 1, down 1, 2, 3, 4. Let's test the point out 1, down 4 in both of these equations. And you can test them in the rearranged versions. That's fine. So negative 4 less than or equal to negative 3 times 1 plus 5. Let's see. That would be 5 minus 3 is 2. 2 is definitely greater than negative 4. Check. All right. Over here, we've got negative 4 is less than 2 times 1 minus 4. 4 minus 2 is 2, which is also greater than negative 4. Check. We actually figured it out. It's true for both, okay? So if you were worried about it, you can always pick a point in that spot and test it out real quick with a little mental calculation. Okay. Yep, moving right along to this next one. We have another weird situation. We have y equals. This is the line where all of the y's equal negative 1. It is greater than or equal to, so it will be a solid negative 1. And it would be all of this stuff, but I'm not going to graph that until I graph my other one as well. All right. Nope, this x and y intercept actually wouldn't be that bad. So let's do this standard format version. Plug in 0 for this. You would get 3y. And so y is greater than or equal to negative 2. I'm sorry, positive 2. 0, comma 2 is one of them. If you plug in 0 for the other one, you have to divide by negative 6. And so you get x is less than or equal to negative 2. I'm sorry, divide by negative 3, not negative 6. Divide by negative 3, you get negative 2. And so we get negative 2, comma 0. Now, these are points, okay, and it's equal to, right? So even if it does flip around, that doesn't change your x and y intercept point. Remember, that part affects your shading. And your shading doesn't have to do anything with the line, okay? So I've got back to and up to. There's my other solid line. Beautiful. Now I have to figure out which one of these 4 zones, 1, 2, 3, and 4, could it possibly be? Well, we already figured out that these bottom 2 couldn't possibly be it because it's y is greater than. I'm thinking, I don't know, 50-50 shot. It's in standard form. So, I mean, we never We had to turn it around once, but didn't have to turn around the other time, so I'm just going to go with 0, 0, because that's easy to plug in. 0, 0 is greater than 6. That is not a true statement. 0 is not greater than or equal to 6. So it can't be that side. I don't really need to test another one, but I can if I want to. I could test a different point in the other zone, and I would get something that is true. Okay, so there is my finished product. All right, let's do this next one here. Both standard form, both easy y-intercept versions. I'll do one y-intercept way, the other one, one standard form, 1 point slope form. One standard form, 1 point slope form. So let's start with this as standard form. And really with the y-intercepts, you could just kind of cover up with your finger the second one. So like plugging in 0 for y would make it this. See how the y part just drops away? That's why we like that one. That would be 4. So x is 4 when y is 0. And by that same logic, y is 2. So we have out 4 and then 2. It is strictly less than. Okay, it is strictly less than. So I'm going to do dotted line, not equal to. And then just for future reference, I'm going to put that down there. Okay, then the next one. Next one I can rearrange. Just, because I could do it both ways. Let's see, that's 12y. I'm going to zoom in here. So 12y is greater than or equal to negative 6x plus 24. If I divide by a positive 12, then I don't need to worry about switching the signs. Oh, see, I don't really like that point. Plus 12, that's kind of hard. Maybe I'll use a different one. If I plug in 6, no, that's not going to get me. Let's see. 6 divided by 2 is 3. Maybe if I plug in, what would give me 0? I don't know. Maybe plug in y equals 0. Let's do that. 0 greater than or equal to. So negative 12 times 24. That's not going to help me either. How about plug in? Oh, because that's a 2. Duh, I was like, why is this being so complicated? But that's exactly what happens in math all the time. And I love making mistakes on videos so that you guys can see that. Like, people make mistakes. It's fine. So divide by 12, you don't get 12, you get 2. Up to, for the y-intercept, is a lot easier to graph. So let's go with red. Up to, oh, hey, cool. They have a matching point. That's nice. And then down 1 over 2 would be here. Hey, wait a minute. These are the same line. Well, that's awkward. But this one is equal to. So I can fill in all of the equal to's there. Lovely, lovely. And, oh, but it's greater than. So it's all over here. Whoa. Hey, wait a minute. Wait a minute, my friends. These are the same equation, but because of the inequality signs, none of this matches. Check this out. Where is the overlap here? Where do you see both blue and red? In the shading, nowhere. There's no overlap between the red and blue, okay? But then even on the line, one is not equal to and the other one is equal to. Those aren't the same. There's no place where this overlaps. This is a no solution problem. Those tricky tricksters. Check that out. So it does happen. Very few situations. This is almost like the one where it happens, but it can happen. All right, cool. The last thing we're going to do is a word problem. It doesn't seem like this would be something that would actually be very applicable in real life, but it is. It is very, very applicable when it comes to cost constraints. So if you ever do plan on going into business, you end up dealing with this stuff a lot. Okay, but let's take a look at something maybe a little more on our current level. Janessa is creating props for school play. So our current lifestyles right now. There are furniture and handheld props to make. she must construct a prop out of wood. It takes 10 hours to construct a furniture piece and 6 hours to construct a handheld prop, on average probably. She has a maximum of 102 hours to spend constructing. Next, she must paint the props. It takes 11 hours to paint a piece of furniture and 12 hours to paint a handheld prop. Why 12 hours? Maybe detail or something? I don't know. But it takes longer to paint the handheld ones. She only has 123 hours to paint all the props. Graph all the possible solutions of Janessa could have Janessa could have when creating the props and the furniture. Sorry, typo there. That Janessa could have. So this is kind of a situation where first you have one constraint. We call these constraints. Okay. You are limited by your amount of time. Janessa only has 102 hours to construct these props. Okay, why it's 102 hours? Maybe she did a math ahead of time, right? She has 3 days or whatever it is. Actually, how many is that? I'm curious. Divided by 24 is 4.5 days, 4 and a little bit more days. So she's only got that much time. And it takes 10 hours to construct a piece of furniture and 6 hours to make a prop. So does she have enough time to make all of it is really her question. We don't know how many she's going to need. Okay, we don't know if there's going to be more. Maybe they want more handheld props. Maybe all of a sudden they decide they don't need this piece of furniture. So she's just seeing how many combinations she can make. All right. One such combination. So I don't know. Maybe we need to define some variables here. Let's call these F and let's call these H. Okay. So one such combination could be 10 hours for 2 furniture pieces. 20 hours there. Could be plus, I don't know, 3 hours or three handheld props. It's a very small play, very small play. That's one combination that would be within our time frame. 20 plus 18 is definitely within our 102 hours. And so let's convert that to math as well. What would that convert to? Is it going to be greater than 102 hours that we want, equal to, or less than? If it's within our time frame, it's going to be less than 102 hours. Okay, so we're thinking that's okay. And this is true, right? So 2, 3 is one of our constraints. In this case, our graph is going to be F and H. Our graph is not going to be X and Y, and that's okay. That's okay. This is just one combination that could be true. But that's probably not all that she could do. She could probably rev up furniture pieces to like 3, 4, 5, 6, 7, 8, 9, 10. But then what happens to her handheld props? Like how many can she still sneak in there? Could she sneak up more handheld props? Could she do both, right? And that's where you start to see this kind of zone shading idea, right? There's lots of different combinations when you start changing both of them. And so let's just do this. Let's take away our originally chosen one, or I guess we could just, let's just copy and paste it. But let's change 2 and 3 to just F and H, variables that we could change, the 2 variables. And we've created the first constraint. That's our first constraint equation. For painting the props, you get a very similar situation. She only has 123 hours to paint the props. Maybe that's all the time that she's allowed access to the paint. Okay, maybe it's they rent special paints or something like that for hours on end. I don't know. Sounds like 11 times 12-hour periods, whatever. But she knows it takes on average this much time to paint each one. And so again, she's presented with that combination idea. Can she paint more furniture, less handheld? Does she have to paint more props? Like what number is she going to get? Now you would assume for the play, they're going to be the same amount, right? But, we don't have to limit ourselves to that kind of thinking. We're not going to say just because she only makes 10 pieces of furniture, do you mean she has to paint 10 pieces of furniture? Okay, so we're going to keep it nice and loosey-goosey. But again, we see that F and we see that H, right? Those handheld, 11 hour per furniture and 12 hour per handheld. And then we see again that maximum, she only has 123 hours, and so it has to be less than 123. And now we see our intersection, our system. Okay. Now there are 2 more constraints here that are not from the problem itself, but from the fact that we live in the real world. Okay. We only had 2 equations. So you might think, oh, well, I'll just have two equations, right? But we're talking about furniture now. Can I have anything down here for furniture? No, you can't have negative furniture. And so I also have the constraint that f itself has to be greater than or equal to 0. That is another constraint. Similar, almost exactly the same argument. Can you have a negative handheld prop? Can you start like making negative props? No. Can you make 0 props? Yes, she could spend her whole time making furniture pieces. But she can't make negative ones. That doesn't make sense. And so we're limited to this first quadrant here as well. We actually have 4 separate constraints. We have 1, 2, 3, 4. That's a really horrible swooshy line, but those are 4 separate things that we have to keep in mind. And the intersection of all of those is going to be the only times and the only combinations she has for time. Okay. So first and foremost, let's graph these bottom 2. We'll graph these ones. Here's f is less than or equal to 0, greater than or equal to 0, pardon me. So I can't go down there. And then I also can't go to the left. All right, there's my first 2 constraints. Now you can see why we maybe spent a little time on those weird ones, right? Because as soon as you hit the real world, that's usually a constraint you see a lot. 10.2 is not the best y-intercept, x-intercept, so I think I'm going to change this so that I set it up so that h is similar to y. So I'm going to do hmx plus b, HMF plus B for, okay? So slope-intercept form is basically what I'm going to do here. But I'm going to take it down here. So 10F plus 6H is less than 102. And we're going to move that 10 over, negative 10F plus 102, and then divide everything by 6. And that's still not great. But 10 divided by 6, yeah, it's non-terminating. So I'm just going to reduce it into 5/3. And then 102 divided by 6 is 17. Okay, obviously my scale of 1, 2, 3, 4, 5 here is not going to work. So I'm going to have to change the scale a little bit. I'm going to change the scale to being out of 10. So 10, 20, 30, 40, 50. 10, 20, 30, 40, 50. And I think I'm going to rearrange the second equation as well before I go graphing to make sure it actually can do that one as well. This is a really horrible plus sign, so I'm going to do plus. There we go. All right, so the second equation, no, we'll do green, is 11F plus 12H less than or equal to 123. 12H, these are almost exactly the same moves. 123, and then divide by 12, we get 11/12. What a horrible slope, but that's okay. Negative 11/12 F plus 11. Nope. Divided by 12 is 10.25. So that's not that bad as a decimal. Hey, mixed. What's 11 over 12? Nope, that one's not terminating. So, cool. That's ugly. But it does fit on my scale, so we're going to have to graph this the best we can. Awesome. Let's start with the red one. Let's go ahead and graph up 17 and then down. It's not letting me grab it. There we go. And then down 5 and over 3, or down 10 and over 6. So I'm going to go down 10 and over 6. And there we are. Okay. It is equal to, I mean, you can have equal to number of hours, right? Totally have an equal to. The green one was up 10.25, so like there. And then down 11 and over 12. So, yep, down 11 and over 12. So like here. Again, not super accurate. On computer would be better. And then it was less than both of those. So less than both of those, but greater than the axes is this teeny tiny window. Oh my goodness, she does not have that many combinations. She has 123 hours to paint, and she has that itty bitty little combination window. Look at that. So you wouldn't think that it would be that constricted, that would be so constrained and confined, but it's true. As soon as you have a lot more, however many constraints you have, you're going to get a lot more narrow of a window. So interesting there. All right, that wraps it up for inequalities in two variables. If you have any questions, reach out to your teacher. Otherwise, I'll see you in 3.5.